Lecture 13, set 8, we will talk about fixed point numbers and how arithmetic operations are done on them. So fixed point number representation system, it's used for integers and it's used for rational numbers of the form a divided by 2 to the power f. So for example, if you have only one bit for your for a representation after the floating point, that means that it can be only a 0 or 1. It means that you can have a notion of a half. If you have 2 bits, then you could have notion of a quarter. If you have 3 bits, then you could have a notion of 0.125 and so on and so forth. So before using the system in real life, we have to agree on the number of points that go after the fixed point. So if we, for example, say that there's only one number after the fixed point, that means that we can only present the number and half. If there are, we have more than one bit, like 2 bit, 3 bit after the floating point, then this could be done. This has to be agreed upon. The binary point, the bottom line is the binary point is not a part of representation, and this is intentional, because if we don't think of the binary point as being a part of the representation, as you will see, we will be able to do the regular operations as we were doing before on these numbers and still get valid results. And this is something that is very useful in real life. For example, if you're representing 7.5 in base 10 using an 8-bit binary representation with 4 integer bit and 4 fraction bits, what we could do is we could write this as a number in 7, which is 0, 1, 1, 1, and then the half, which was, as I mentioned, like only one bit after the fraction is showing you the half. So this becomes 1, 0, 0, 0, which shows you the half. So if we want to represent this 7.5, we just take the first 4 bits and represent a 7, and then 0.5 is represented by the fraction bits here. So the way this is interpreted is that this is 2 to the power 3, this is 2 to the power 2, this is 2 to the power 1, this is 2 to the power 0, this is 2 to the power minus 1, 2 to the power minus 2, 2 to the power minus 3, and 2 to the power minus 4. And as you know, 2 to the power minus 1 is 1/2. So this is basically the 1/2 portion of this number. Similar to integers, the negative fractional number can be represented in 2 ways. You could use the sign or magnitude notation, which is less used, but you could also use the 2's complement notation. And if we have this 7.5, which we represented in using this 8 bits, all what you do if you're trying to convert this to a 2's complement is just do the 2's complement steps. So remember that we had that that number, and then the 2's complement is basically taking this number, inverting the bits, adding a 1. So we take the 7.5, which we computed in the 2 slides ago, then we invert everything, and then we add a 1, then we get the number here. So this becomes really straightforward. It's exactly the same as we were representing a number. One thing that becomes important here is thinking about the precision, because as we mentioned, like the number of bits that you choose after the floating point is fixed. You can't change it. So that means that you're at most having we are basically quantizing things, and we have at most that much accuracy. So if we have 2 bits after the floating point, the most accurate you could become is 0.25. If you have 4 bits after that, the most accurate you would become is 1 over 2 to the power 4, which is 1 over 16. So there's always this notion of a quantization, and you have to be making sure that you are chosen the range correctly and this precision. And sometimes this can become problematic if you're talking about, for example, some of the signal processing functions where we have this accumulation over time. This can also hurt precision. So this choosing the right number is super important in those type of scenarios. And in DSPs, also, which is a signal processing units that are usually kind of pre-computed, we need to also be very careful of that, because in the DSPs, where you try to this computation of the values, this precision really impacts the signal to noise ratio, because the precision can get accumulated over the computation, and then this can affect the dynamic range of which signals you could show in which range. And typically, it's typical to perform simulation to evaluate the effect. So as I said, fixed point representation is useful for some tasks. It may not be the best choice for many different tasks. And in particular, if you're trying to do that, you need to be very careful about the ranges. And one way to do this is try to use kind of vectors that have this scaling implied, where the index range matches the power of weights. So if we say input is 5 to -7, that means we have we're going all the way to -7, and on this range to 5, which means that we have -7 points after the floating point and 5 bits before that. So that gives you a range of the signals, and that can help you do these additions more carefully. And in order to do this fixed point operations, it's best if we just use the integer hardware, so we don't need to define new hardware. And as I said, in two's complement system, you could easily do these operations as before, so it doesn't really impact that representation, or that place where you agree on putting that floating point, or that agreement that we have for the range. None of these really impacts the way we are doing the computation, and that's the beautiful part about this. In the last set of the lecture 13, we'll be talking about floating point numbers and how they can be computed efficiently and what are the standards for those.